Welcome to 2.5 Proofs of Congruence. Remember in 2.4 we talked about 3 postulates and we also learned about one other theorem. So the 3 postulates, these would guarantee congruency, and we wanted to know if we could come up with more shortcuts. So we asked, instead of having the side included, can we have a situation where the side isn't included? And we saw that yes, it worked. So these 3 postulates guaranteed congruency, and this theorem guaranteed congruency. But we also wondered if angle, 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 and side, side angle guaranteed congruency, and we determined it didn't, because there were some situations where it was congruent and some situations where they were congruent. So angle, 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 side, side angle would not work because they don't always guarantee congruency. So what similarity do you see between these 4 shortcuts? Well, you see that there's 3 parts, right? Because there are 3 letters. That means you need 3 parts or 3 measurements to determine congruency. Now, you won't always be given all 3 parts. Sometimes you'll be given 1 or 2 parts, and you'll have to decide which parts are congruent based on other things you've already learned. So let's get into some examples. We want to prove that triangle ABC is congruent to triangle EDC. Okay, but let's try to prove that first. So what is already given? We're given that segment AC is congruent to segment EC, and you see that represented by the hash marks, okay? We're also given that segment BC is congruent to segment CD, and that is represented by those other hash marks right here. Okay, so these are congruent and these are congruent to each other. So we write the statement here, and it's given. So this is called a 2-column proof, where one side has the statement and the other side will write a reason. So this is a statement, and our reason is that it's already given based on the figure because there are hash marks. Well, what else do we know? Let's think back to, remember the vertical angle theorem? You can recognize that. You should be able to recognize it right away. You see that these 2 angles are on opposite sides. That means they are congruent to each other. So our second statement would be angle ACB is congruent to angle ECD. And what is the reason? Like I said, it's the vertical angle theorem. Angle theorem, which states that angles that are on opposite sides of each other are congruent to each other. Okay, so what else can we determine from this figure? Well, what do you recognize? You recognize side, angle, side for one triangle is congruent to a side, angle, side for another triangle. So that is actually one of the postulates we learned. So we can actually conclude that triangle CBA is congruent to triangle CDE. And what is the reason? What is the reason? It is according to the side, angle, side postulate. And remember, when we write a congruent statement, the vertices have to correspond to each other. So C corresponds to C, B corresponds to D, B and D, and A corresponds to E, A and E. Okay? So do you see how we started off just knowing 2 pieces of information where we are given 2 sides, right? But like I said, up here, based on the 3 postulates and the theorem, we need 3 pieces of information. So we figured out a 3rd piece of information based on what we've learned before, which was the vertical angle theorem. Okay, so you see how a lot of what we learned before is going to become relevant now, and they are all connected to each other. So we just proved that this triangle is congruent to this triangle based on the information given and previous things we have learned. So let's get into another example. We want to prove the congruence of ABC and FED. Okay, so what is already given? We're given that segment AB is parallel to segment EF. Segment BC is perpendicular to segment AB, right? This notation indicates parallel lines, and this notation, upside down T, indicates perpendicular lines. What else are we given? Segment DE is perpendicular to segment EF. We can see that because they meet at a right angle. So it is because of the right angle in the figure, we can conclude that these are perpendicular to each other. So that is why we're writing that it's given, because in the figure we see that it's already given. We also know that segment ED is congruent to segment BC because of the hash marks, okay? So all of this information is already given based on the figure we see and what the problem already tells us, okay? So what else can we determine? Well, we can see that angle E is congruent to angle B because they're represented by these squares, which indicates that they are right angles, okay? So the reason is that they are both right angles. Okay, what else can we see? We see that angle F is congruent to angle A. Well, how do we know that? Well, importantly, it states here that segment AB is parallel to segment EF. But what do you notice about segment FA? Doesn't this remind you of a transversal, right? If this continues all along, we see that we have two parallel lines and it's cut by this transversal right here, okay? If we were to try to erase this, now we can clearly see it looks like parallel lines cut by a transversal. And what did we learn about transversals? We learned that transversals created three special pairs of angles. And one that you can identify in this figure are angle F, and angle A. What are these again? These are alternate interior angles because they're on the inside of the parallel lines, where these are the parallel lines, and alternate because they're on opposite sides of the transversal, right? This is on the top of the transversal, and this is below the transversal. So these two angles are alternate interior angles, and what did we learn about alternate interior angles? We learned that they were congruent to each other. So we know that angle F is congruent to angle A because of alternate interior angles. So now what do you see? We see angle, angle, side, and that was one of the theorems that we learned. So based on the theorem, we can conclude that triangle ABC is congruent to triangle FED. Again, whenever you write a congruent statement, the vertices need to correspond to each other, right? Vertex A corresponds to vertex F. Vertex B corresponds to vertex E because they're both right angles, and vertex C corresponds to vertex D. So this is our congruent statement, and how did we determine congruency? Based on the angle, side theorem. And what is significant? The side is not included because here's our angle, and here's our side. It is not between the angles, so it's not an included side. So this would be angle, side theorem. It wouldn't be angle, side, angle. Okay? Now let's take a look at our last example. We want to prove congruence of these two triangles, right? So what is already given? We're given that triangle ABC is an isosceles triangle. We're also given that D is the midpoint of AC. Okay, so here's our statements, and here it's given. Now remember, what is the significance of midpoint? Remember, for midpoint, they're in the middle of a segment, so it will divide the segment into two equal parts, those two equal parts being AD and DC. So what can we conclude based on what we were just given? We can actually conclude that segment AD is congruent to segment DC. And how can we conclude that? Because we already know that D is the midpoint, and we learned previously that midpoint will cut a segment into two equal parts. D is the midpoint, and it cuts segment AC, yes, segment AC into two equal parts. What is another thing we notice? We notice that segment AB is congruent to segment BC. How do we know that? Because we know that ABC is an isosceles triangle, which means at least two sides are congruent, and where that third side is the base, okay? We see that this is the base, so these two sides are the ones that must be congruent to each other. So let's draw hash marks. So how did we know that segment AB is congruent to segment BC? Because we know that isosceles triangles have two congruent sides. Okay? We don't have enough information yet. Oh right, I forgot. Segment AD is congruent to DC, so we need to write hash marks. Again, we only have two pieces of information. We only know two sides. We need three pieces of information to prove congruency based on the four shortcuts we learned. So what else do we know? Well, remember the congruence properties we learned? Reflexive, symmetric, and transitive? Well, we can actually use one of those properties in this case. Remember I said, what is the significance of this of the three properties? I said the significance was that we would need it to use it for proofs, and this is when we are going to use it. So we can say segment BD is congruent to itself. Now it's silly to say, but it's actually important in this case. And how did we draw that conclusion? Segment BD is congruent to itself. This is the reflexive property. Now you see we have three pieces of information. 1, 2, three hash marks. There you go. 1, 2, and 3. Now what kind of postulate does this remind you of? This looks like side, side, side. So now we have three pieces of information and it fits one of our shortcuts. So now we can conclude that triangle ABD is congruent to triangle CBD. And what was the reason? The reason is the side, side, side postulate. Postulate. So you see in all three examples that we just went over, you see this common theme where we are given some starting information and we have to determine some congruency and come up with at least three parts so that we can apply one of the four shortcuts we learned to determine congruency. Because the purpose of the shortcuts is to determine congruency without knowing all the information. So you see we learned stuff we learned previously, such as the vertical angle theorem, isosceles triangles, and reflexive properties. We use those to gather information, find at least three pieces of information or three parts in order to determine congruency.